That was a surprisingly tough act to follow. But I'm Delaney Miller.
And I'm Guan and we are from a team, part of the Stanford Biomechatronics Laboratory that's interested in augmenting running. Today we'll be talking about a study that was actually largely led by Kirby Whitty and Peter Fierce, and in collaboration with Alison Sheets from Nike. We'll be talking about optimizing the energy economy of human running with powered and unpowered ankle exoskeleton assistance. So I'll jump straight into talking a bit about the motivations behind the study and some of the previous studies done. Why optimize running exoskeletons? Many reasons, but here are our top 3 reasons. It'll be exciting if we are able to increase the participation in running, either by making running easier and reducing fatigue. We are also interested in comparing the different assistance strategies, namely powered versus passive assistance strategies, because both of these paradigms have shown good energy reductions in the past. If we are able to identify ideal assistance strategies, we can then use this to inform the design of an untethered device. So these are some of the devices I think a lot of us are familiar with that have shown a lot of success in the past. For passive devices, we have groups that use passive springs in the shoe, between the ankles and at the hips to get 4%, 6.2%, and 8% metabolic cost reductions. For power devices, there is an fully untethered hip exoskeleton that achieved 3.9% metabolic reductions compared to no exoskeleton. And our group has also achieved some metabolic reductions with our tethered powered ankle exoskeleton, although it's just part of an N=1 pilot test, but this definitely motivated our current push for this study that we're going to talk about. So each of these paradigms have different advantages. For passive devices, they tend to be a lot simpler, a lot more lightweight. Also, it might be easier to adapt to because they tend to mimic the spring-like behavior of running. For powered devices, it gives us the ability to inject positive work, and this potentially allows us to get larger metabolic improvements.
So now I'm going to talk a little bit more about our experiment itself and the protocol. So you have probably seen other talks come out of our lab that show this figure, but we use an ankle emulator, exoskeleton emulator system that uses off-board motors. They're connected by Bowden cables to the exoskeleton, and we can apply torques and plantar flexion about the ankle joint using that system. So this allows us to try a wide variety of assistance strategies and then determine what the optimal assistance strategy is for the individual user. And how do we do that? Human in the loop optimization. Sorry, Steve. So the way we do this is that we can create desired assistance curves, either based on time or based on ankle angle, and we define a set number of parameters to set the shape of that curve. Then we can generate a wide variety of control laws. We test these control laws on the human user, and we measure metabolic rate as our cost function, and then we use a covariance matrix adaptation evolution strategy algorithm to figure out what the best control laws are and proceed to the next generation of control laws based on those metabolic costs. So in this experiment, we are interested in comparing 2 different types of assistance. The first is that we can use the ankle emulators, ankle exoskeleton emulators, as a passive spring-like system. And we do that by defining 3 parameters on a torque versus angle curve. The first parameter is going to be the torque at maximum dorsiflexion. So if you think of a spring being attached kind of along the Achilles tendon, that maximum torque will occur at the max plantar or max dorsiflexion angle. Then we can define the spring as either a stiffening, a softening, or a linear spring through a shape constant. And finally, we define an engagement angle, which is the plantar flexion angle at which the device no longer applies an assistive torque. For our powered assistance curve, we introduce 4 parameters. 3 of those parameters are timing based. So we have a time of torque onset, which is a percentage of stance time, because we don't want to apply torques during swing. We also have a timing of the peak torque and a timing of the torque offset. Our 4th parameter is on the magnitude of the peak torque. And you can see that these colored regions demonstrate the allowable ranges, so we make sure we're never applying assistance strategies that could be uncomfortable or painful to the user. So yeah, as I mentioned, this allows us to create a wide range of control laws so we can test these on the user and then in real time figure out what the optimal strategy would be. So in this study, we had 11 subjects. That's Steve again. And they were all recreational runners who had completed a marathon, and they were all natural heel strikers, so that our stance detection sensors in the heel would register. All the runners also ran at 6 miles per hour or 2.7 meters per second. So it was kind of like a joggish run. They weren't sprinting, I guess. So in the first day, we wanted our participants to experience both controllers before going through human-in-the-loop optimization. So in random order, they experienced the spring-like controller and the powered controller. We put them in the device for 5 minutes of running with 0 torque to just get used to it, then 5 minutes of a sort of generic assistance law, and then a generation of sample control laws, and I'll explain that in detail a little later. The same was true for the powered assistance mode. On the second and third day, they either experienced the spring-like optimization or the powered optimization. So for the spring-like optimization, each generation of control laws had 7 control laws that were each for 2 minutes. We collected metabolic data, progressed to the next generation, and we completed 4 generations of running. The same was true for the powered assistants. They were experiencing 8 control laws. That's largely due to the difference in number of parameters to construct our curves in CMAES. Finally, on the last day, we compared our optimal spring-like assistance profile, optimal powered conditions to 0 torque mode and to normal shoe running. And the participants ran in each of these conditions for 6 minutes. We collected metabolic data from the last 3 minutes of each trial, and we performed these in a randomized double reversal order to make sure we are accounting for factors such as fatigue.
So we applied this long protocol to all 11 different subjects, and here are some of the results. First, you'll take a look at the optimized torque profiles. So here in each of these colored lines represent one of the 11 subjects. So we have 11 colored lines shown here. If you just look at the first row, this is the results from the powered assistance profiles. On the y-axis, you have the torque assistance normalized to subject mass. So it's Newton meters per kilo. The plot on the left is torque against time as a percentage of stance period. You can see the dotted gray line shown. That's the mapping of the biological ankle at 50% scale, just as a comparison. And you can see that obviously the optimized profiles seem to be tending towards somewhere a lot on the right of that peak profile. The plot on the right is torque against ankle angle. And this plot is useful because the area under each of these curves tells us about the amount of energy injected into the system by the powered assistance strategy. At the bottom, we see the profiles for the spring-like assistance. On the left, we see how the exoskeleton kind of tracks the ankle motion, just as like a spring-like kind of performance. And on the right, the torque profile against ankle angle. What's useful to see here is the lack of a work loop, which shows us that we are accurately kind of recreating this kind of non-energy injecting passive spring. So here are some of the metabolic cost results. We have 4 things plotted here. The results for 0 torque assistance, the optimal spring-like assistance, optimal power assistance, and for normal shoes. If you compare against 0 torque, the spring-like assistance gave us a 2.2% reduction, and the powered assistance gave us a 24.7% reduction. Compared to normal shoes, the spring-like performance actually was worse off, while the powered assistance gave us a 14.5% reduction overall.
So we have a few key takeaways from this study. One was that powered ankle exoskeletons seem to perform quite well with our emulator systems to reduce the metabolic cost of running. One thing that was really interesting to us was that all of the subjects optimized to peak torques that occurred after the biological peak torque. And we believe that this is probably due to the force-velocity relationship of the soleus. In late stance, your force capacity is limited, and that's where the exoskeleton would assist in applying a large torque. We also found passive ankle assistance was pretty ineffective, and it could be a result of partially due to our hardware and how we parameterized that spring. But we did notice that the peaks occurred earlier with the passive assistance than with the powered assistance, which seemed to be suboptimal. We also were not injecting work, so we see that these passive hip exoskeletons seem to perform quite well, and that could be due to the fact that the hip has about 0 net joint work. Finally, we can see that these emulators are a really good tool to give us a sense of what might be really good for an untethered running device, which is the direction we hope to head in next. Thank you.
Can the optimization discover no assistance?
Yeah, so that peak torque parameter can go all the way down to 0. So they could optimize to nothing.
And then, so it looked like there was substantial, for the spring-like one, there was substantial, yeah, so like, there was substantial assistance being provided, substantial, I guess, spring constants. But then the savings were nearly negligible. So those almost seem like they're incompatible.
So I guess you can imagine, let me know if I'm answering your question correctly, but I'm imagining that if you imagine that at the peak dorsiflexion, that's actually not, that's where the spring will be applying the most assistance, and that's not actually where you tend to have peak push-off. So this, in our current setup of our passive spring system, although it's doing quite a lot of, it's applying a huge force at the dorsiflexion angle, that's not the ideal point. So the power profile manages to give you your peak assistance where you really want it, which is somewhere mid-planning and dorsiflexion.
Yeah, I think I was saying something a little different, which is just like there's incompatible is not the right word, so I guess it's totally possible that there's multiple minimum with the same, but you have this like, without assistance at all, it's the savings is 0%, right, because that's your reference value. And then with the spring added, it was nearly 0, let's call it 0, but
What?
it found a solution,
2%, yeah.
Yeah, maybe that's not 0 for Nike, that's true, right? It's like, the 4% shoe is amazing, right? So that's a good point. So, but if we call it 0, then the idea is it's finding another 0 solution but with a non-zero spring.
So another thing that maybe could be related to that, and I don't know the exact subject breakdown, but you can see some subjects actually optimize to very, very low torques with the passive assistance, and it's possible that they saw some sort of, I guess, metabolic disadvantage to using the spring-like assistance, whereas some of our participants did actually experience significant metabolic reductions using the spring-like assistance. Another thing is that when you heel strike, you're roughly a 0 angle, and then you go into dorsiflexion. That could actually be like a sort of metabolic cost when you're engaging the spring, and then as you push into plantar flexion, then you're getting the metabolic benefit. So.
Can I just add 2 quick things to that? So if there is a little bit of savings, then you can still get this big intervention. So you're not getting a lot of bang for your buck, but the optimizer's still moving in that direction. Yeah. And the second thing is, we ran this for 4 generations, which, based on Katie Poggensy's work that she presented yesterday, over 20 generations, it looks like that's not long enough to fully converge. So it may be that some of these trajectories would have gone to 0, say, for some of these participants with more time.
I apologize if you said this, but do you allow the optimizer to choose the 0 set point in the spring as well?
So are you referring to the point where it's not applying your torque?
Yes.
Yeah, so that is the engagement angle over here. So we allow that to shift within the range in red.
So what do you think it means that it seems like everything picked close to 0 or 0? Is there something to take away there?
That means that in plantar flexion, it's not. The results. Right, so you're saying that in this, I disagree that it's around 0. It kind of is plateaued there, but there you see the curves kind of going somewhere like between -5 and like up to 20. So I think it just scopes quite a wide range. But yeah.
I'm imagining you fitting a line to your upper right plot, right, where that, if you did some sort of...
Oh, for the upper right plot? You're saying this? So for the upper right plot, I think that's more a function of, so the top starts getting, so for the upper right plot, this torque angle relationship, I think that's more because when you're running, you kind of hit the ground almost with your leg under you with an almost neutral angle.
I'm trying to channel what I've like learned from Johnny Godowski and Jerry along the way, which is if you look at this like torque angle plot, and you fit a line to it, then it's spring-like, and you should put a spring there. And so I'm trying to imagine putting a line on your upper right plot, and whether that matches up with the bottom right plot. If that makes sense.
Oh, you mean like the beginning half of the upper right plot?
Yeah, you have the beginning and the second, so that's hard.
Looks like a vertical line. Block the
Sean,
ankle.
the vertical line barely reaches anywhere. Like if you draw a vertical line there, it's like barely getting to anywhere near the peak top. So I feel like you'll only be assisting that really tiny.
Are you reading those ones clockwise or counterclockwise?
It's kind of counterclockwise. So you follow, you kind of you hit the ground kind of at 0, and then you go to like a bit of dorsiflexion, right? So you're going left, and then you're applying more torque, you're going around, and then you come back down and push up. So that's what the loop is.
But it would be clockwise.
Sorry.
Just describe it.
Sorry, I'm like,
Yeah, so negative is dorsiflexion angle and positive is plantar flexion angle.
Please, clockwise or counterclockwise?
The way we parameterize the torque versus time, it could have had patterns that had more of a spring-like behavior at first, so more sort of negative work before it loops around and does positive work, and it doesn't, as you see. It's mostly, almost entirely positive work, right? So that suggests that in this case, spring-like assistance really isn't the best way to improve energy economy of running. That parallel spring isn't going to help you much here, I think.
There's a question here.
You know, I was wondering if you looked at how they changed at the knee, specifically knee extension, with the assistance, especially with these really bent knees during running, and then you're providing extra torque at the ankle, then something might have changed at the knee, and is that factored into their adaptation strategy?
So I don't believe in this study they collected any sort of kinematic data on, on the knee or anything else.
That's a very good point, though. But I know that now when she runs in the exercise, you do notice she gets a little bit of a crouch bit too. But it definitely affects the kinetics. But as part of the study, we did look at it. But that's a good point. There's a question in the back.
Aaron, mathematics. Can you comment on power consumption for the powered assistance and maybe the correlation between power consumption and metabolic screens? Like, what is this going to look like when you make a tetherless version?
Good question, because we're currently thinking along the lines of heading towards the untethered version. For this study itself, we have the numbers in really tiny font somewhere. Let's see. So we have the numbers for optimal assistance. So we have the peak torque normalized to mass of about 0.7 Newton-meters. And then the work injection is about 0.48 watts per kg. But yeah, we're currently specking out some stuff with some untethered devices, and I think that question is also interesting because for the untethered device, we might not be constrained to this same actuation, which is like a bone cable system. So we're actually exploring other kinds of actuation systems, and that really changes. Like with the gear ratio, I think that changes the consumption a lot. All right, let's take one more question. Set up, David.
My question was really, really close to that. So you've got the mean mechanical power of 0.48.
Yeah.
And I'm thinking about like the idea of a reverse efficiency, like how much metabolic power is saved per unit of mechanical power injected.
We have a lot. That's also something we're currently exploring further.
You can get us our numbers and I can talk to you separately.
I do actually have one last question.
Yes.
Can you guys tell everybody what this system is called?
T-Rexo, tethered running exo.
I love it. Okay. Let's take the speakers.